Okay, good morning. So let us start today's lesson. So again, we want to continue with combinatorics. So far, we have considered the cases in which the order matters, and then we call them permutations. Now we want to talk about arrangements or items in which the order doesn't matter, but the combination of the objects as a group matters. Okay, so uh, for example, let me say that I have n distinct objects. Yes, and then I want to choose. This is the important word here. I want to choose R of them. Okay, and the combination of the chosen items are important, not the order in which I arrange them. So R is assumed to be a number maximally n and minimally 1. Of course, R and N are natural numbers. So I want to choose R of them in which the order does not matter. Each one of those items is called a R combination. R combination. So for example, if I give you these letters A, B, C, D, and E, these are distinct objects, 5 of them I have. So in this problem, n is 5. So I ask you to write all 3 combinations. Okay, so I just want you to know what is the meaning of the R combination. So here I am asking you to write down all 3 combinations. So what do I mean by this? I mean, first you have to choose 3 items, okay, and write them once, no matter in which order you write them. So for example, if I take A, B, C, in 3 permutations, I choose A, B, C, but I start considering all possible arrangements. But in the combination, I just choose them. It doesn't matter if you write A, B, C, B, C, A, or whatever. So this is just 1-3 combination. If you write A, C, B, this is not a new 3 combination. It is the same 3 combination. So you write it only once. Okay? So that is one possibility. What is the other possibility if I want to have 3 combination? I can choose A, B, but instead of choosing C, I can choose D. I can choose A, B, and then I can choose E. These are 3 combinations, so I'm not reordering them. So what can I do next? Let us see if I can write all of them. So what is the next one? So I can keep A and then C and D. I can keep A, C, and E. I can keep A, D, and E. What can I do else? I can keep B, C, D, B, C, E, and then what more? Do you see something else? C, D, E. Yes, there should be one more. What is that? Yes. Do you see any other? I know that by the formula that I have, there should be 10 of them. Do you see anything that I am missing? A, B, C, A, B, D, A, B, E. What? E, B, D. So it is E, B, D is B, D, E. B, D is not there. Yes. Yes. Thank you. So B, D is not there. So these are the 10 ones. Okay? So each one of them is called a 3 combination. The number of 3 combinations is denoted by this symbol, C4 combination. I have 5 distinct objects, and then I want to choose 3 of them. So how we read this? This is called choose 5, 3. Sorry, 5 choose 3. So if you want to read it, you read it 5 choose 3. So this symbol is the number of 3 combinations out of 5 distinct objects. So for example, if I ask you, do you know this number? Yes, because we did it and we can count them, it becomes 10. But of course, the problem is that how can I find this number without writing them down? Okay, so we want to find a formula for this in general. So what do we want to find the formula for? I want to know the number of combinations of n distinct objects if I want to choose r of them. We want to find a formula for this. But is the idea of combination clear? Yes. Okay, so let me try to immediately find the formula for that using this idea that we have here. So for example, here I can have ABC, I can have ABD, I can have, for example, until what BDE as you mentioned, okay? But then let us write all the permutations below them. So for example, I can have AC, B, I can have B, A, C, I can have B, C, A, I can have C, A, B, I can have C, B, A. Okay, and then so the depth of this column is how much? 6, which is coming from 3 factorial, it's a factorial model. So the depth of this column is 3 factorial. Do you agree that the depth of this column is also 3 factorial? The depth of each one of these columns is 3 factorial. In the case of permutation, I have considered them separate, but in the case of combination, all of them becomes only one item. Okay, so the number of columns is the number that I am looking for. Yes, that is exactly, of course, we know that number here in this problem is 10, but if you want to find the formula for it, you should think in this way. So the number of columns is the number of 3 combinations. Yes, but if I ask you how many items you see in this rectangular box, you can calculate it in 2 different ways. One very elementary way, by saying that I have x columns and the depth of each column is 3 factorial. So the number of items on the one hand is x times 3 factorial. This is the number of items here. But on the other hand, we already know the formula for the number of items there. What is that? P of 5 and r, yes? So P of 5 and 3. Yes, is that right? Because if I ask you, what do you see in the table in its totality, you will tell me I see all 3 permutations of 5 distinct objects. Yes, is that right? So on the one hand, based on what we learned before, the number of items in this rectangular table should be this. And on the other hand, it should be the number of columns multiplied by the depth of each column. So these 2 numbers should be equal. So if I ask you what x is nothing except the previous formula divided by an extra 3 factorial. Yes? This is one way. Of course, you can understand that each item has 3 factorials, so you can say that, okay, I divide the previous number by 3 factorial. So in general, if I ask you what is the combination, what is n choose r? So we need to read it in this way, n choose r. What is that? It becomes p, n and r, but divided by r factorial in general. Yes? And then this is why we have a formula for it. So this becomes 1 over r factorial multiplied by p, n, and r, which was n factorial divided by n minus r factorial. So if you combine these 2 fractions, then this is your formula. N choose r is equal to n factorial goes to the numerator divided by the difference of these numbers factorial in the denominator. We also have an extra factor of r factorial. Well, this is when we don't care about the order, only care about the combinations. And there is this symbol is not used in your book. They have used this symbol, which I also like this symbol. I don't know, this is more common. This is more reasonable because C starts is a combination and this is a permutation, so it is really a good notation. But for some reason, in books, in combinatorial books, they denote this mainly by writing something like this. And there is no line in it, okay? So that's two big brackets, and then N and R in vertical way, the bigger number on top, the smaller number below. Okay, so if you see this symbol, it means exactly that. Okay, that's something interesting. It is simple. So let us calculate this now. For example, of course, we know the answer should be 10, but let us calculate this using formula. So 5 factorial goes into the numerator, then I will have a 3 factorial here, and then I have the difference between them, 5 minus 3 factorial. So it becomes 5 factorial divided by 3 factorial times 2 factorial. 5 factorial can be written as 5 times 4 times 3 factorial. This is just 3 factorial, and then 2 factorial is just simply 2. This one and that one are gone. 5, 4 is 20 divided by 2, as expected, is 10. Yes? So this is very simple. Okay, another thing is that, so for example, let us try to test your understanding a little bit. Without calculation, so from now on, I use this more common symbol. So from your intuition, what do you think this number should be? So let us interpret what do I have? I have n distinct objects. I want to see in how many ways I can choose n of them. Yes? One way. Is that understandable? So we predict that it should be 1. Let us calculate. So how should I calculate? This number on top, this number factorial below, and the difference between them 0 factorial. And again, this is a good reason why 0 factorial by convention is 1. Because this is 1, n factorial divided by n factorial is 1. According to our expectations. What do you think this number will be? What is the meaning of this? It means that I have n distinct objects. In how many ways I can choose one of them? Isn't it obvious? I have n students. I want to choose one of them. How many ways I can do that? N ways. So we predict that this should be n. Let us calculate. The number on top, n factorial. This number factorial in the denominator, the difference between them factorial again in the denominator. But then you know how to simplify this. You write n times n minus 1 factorial. 1 factorial is just simply 1, and then you have n minus 1 factorial. These are cancelled, so yes, this is also according to your intuition. But if I ask you what do you expect about this, you cannot say something. Or I don't know, might be you can say something. I have n students, in how many ways I can choose none of them. Yeah, I don't know if this is reasonable or not, but you can say that, okay, I don't choose them, that's the only option. And it turns out to be right, it becomes 1. But some people say that, okay, this doesn't make sense because I cannot choose none of them out of n. But anyway, if you don't like that, consider this as a convention, that this is 1. If you like that idea, so this is according to your intuition. That's up to you. But anyway, I want to show you that this becomes n factorial. If I use the same formula, then I will get the difference between them factorial. And of course, this is 1 because 0 factorial is 1. It is up to you. If you like, you take this as the convention. Or if you think that it is reasonable to say that in how many ways I can choose 0 objects out of n objects, which doesn't make sense that much to my mind, then by that case it becomes 1. Any questions so far? Okay, so one of the main questions that you might face is questions about subsets. Because when you have a set, you remember the order doesn't matter. Okay, so usually subsets and sets are related to combinations. Because automatically from our knowledge in set theory, we know that the order does not matter. So let us try to practice a little bit here. So I give you a set. Let us say A is this set. Set consisting of 1, 2, 3, up to 10. This is the set. I ask you some questions. So number one, how many 3-element subsets? So let me write it in short. So 3-element, the number of 3-element subsets. Number of 3-element subsets. So what is this? So you see, you have 10 distinct objects. It is clear that to write a subset with 3 elements, you need to choose 3 of them. But because of your knowledge from set theory, you know that order doesn't matter. Okay, so when you want to choose and you know that order doesn't matter, that problem is not a permutation problem, is a combination problem. So the answer to this is what? Is simply 10, 10 choose 3. If I insist, you can calculate it. Let me calculate one of them, but usually this is enough in writing in the exam if the calculator is not available. And then you have 10 factorial divided by 3 factorial, the difference between them 7 factorial. And then you know what to do. Instead of 10 factorial, I write 10 times 9 times 8 times 7 factorial divided by 7 factorial. I keep it because it is going to be cancelled. But 3 factorial, I open it up, it becomes 6. 1 times 2 times 3. And then I simplify this one with that one. So for example, here I can simplify this by 3, it becomes 2. This by 3, it becomes 3. This by 2, it becomes 1. This by 2, it becomes 4. So it becomes what? 100 and... So there are 120, and of course on the calculators you have an extra button for the combination as well as you have an extra button for permutation. Any questions so far? So it's probably one of the simplest classical examples how to use combinations. Okay, so let me ask you this question. Number 2, the number of 7-element subsets so that each one contains 1 and 2. So that's also a simple classic example. Here I want to choose 7-element subsets. If there are no constraints, what is the answer? 10 choose 7. But now I have given you some constraints. I want you to choose them in a way that you are certain about the existence of 1 and 2 in all of them that you are choosing. So how can I solve this problem now? Yes? 8 choose 5. Yes. Why do you say that? Because you see that 1 and 2, I don't have any choice. I have to have them. Yes? So 1 and 2 are there. So take 1 and 2, and how many are left? Are 8. But how many choices, free choices I have? Only 5. Yes, because in principle I have to choose 7. Already 1 and 2 are chosen for me, so I don't have 7 degrees of freedom. I have only 5 degrees of freedom. Out of how many elements? 8. So the answer to this is simply 8 choose 5. Yes? Okay, so let us say that how many 5-element subsets, the number of 5-element subsets that contain that contain 1 and 2, but does not contain 3. Let us write 3 and 4. Okay? So, yeah, you can play around with the concepts. This time you want to choose 5 element subsets, but you don't have 5 degrees of freedom. You have 3 degrees of freedom because 1 and 2 have already been chosen for you. But there is also another constraint, so you have to be careful that 3 and 4 is not within your choice. Okay, so how can I solve the problem?
6 choose 3.
So you say 6 choose 3. Let us check. In principle, how many elements I have to choose? 5. 2 of them are already chosen for me. So 1 and 2 are already chosen for me. So I have to choose only 3 of them because out of 5, 2 of them are chosen. I am left with 3 choices. But from which number of elements? Yes? 3 and 4 shouldn't be there. 1 and 2 is already chosen. 3 and 4 are not there. So what is the number of items left for me? 6. And then I want to choose 3 of them. Yes, is that right? So it is not hard. Okay, so let us say that I have another question. Let us say that I have the number of physics math books, number of math books, the number of distinct math books. Let us say that this is 12. And the number of distinct physics books, let us say this is equal to 17. So the question is that in how many ways I can choose 6 physics, 6 math books, and 7 physics books, and put them in a shelf alternatingly. Okay, so I have 12 distinct books, math books, 17 distinct physics books. I want to choose 6 math and 7 physics books, arrange them in a shelf alternatingly. So that's a combination of this new lesson and some of the old lessons. So I want to refresh your memory. Yeah, you can write down your number and then I will ask you. Okay, could you solve it?
Yes.
So this is not a hard problem, okay? The choosing part is today's lesson, yes? Because I think in that way, how many math books you have? 12. What you do first, you choose 6 of them. Imagine that you have 6 math books in your hand. There is no ordering here, okay? So you keep it in your hand. And then you choose 7 books out of 17 and you still keep it in your hand. So there is no ordering yet. So that process, so I would say a stage number 1 is what? Choose 6 math books out of 12. So a stage number 1 can be done in how many ways? This is today's lesson. 12 choose 6. This is the number of ways that I can have my choices for the 6 math books. The stage 1 is done. It means that I have made my mind about which physics math books I should choose. Then stage 2 is what? The story of stage 2 is to choose 7 physics books out of 17 books. So it becomes 17, choose 7. Yes? But now I have these books in my hand. So you can say a stage 1 or a stage 2 are done. Then I want to arrange them now in which order matters because I'm saying it's alternatingly. So it means that order matters. So how should I do that? How many places I need in total? I need 13 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. But because I want to arrange them alternatingly, I should start with a physics book. So this means that the odd ones should be dedicated to physics ones, and the even places should be dedicated to math books. Okay, but so stage number 3 is what? To arrange physics books in odd locations. How many odd locations I have? 7. How many distinct objects I have? 7. So that's the factorial model. So S3 becomes 7 factorial. Yes? And then S4 is what? Which factorial? 6 factorial. Yes? So you could solve this problem using permutation as well, but I don't know, for some reason, for my brain at least, this combination way of thinking is easier. Because in practice, you really want to do it. What do you do in practice? You really choose, and then you go and arrange them. Okay, so that is the human way of doing it. But of course, if I want to ask you what is the final question, you have to multiply all of them. So this becomes 12 what? 6, 17, 7, and then 7 factorial, and then 6 factorial. Yes? If you write that, that is okay. But you know that 17, 7 multiplied by 7 factorial becomes what? Becomes p. Yeah? So this is just a p. And this one multiplied by that is also a p, yes? Because you see here on the board. So when I wrote this, it is still on the board, you see? R factorial multiplied by combination becomes permutation. Yes? So here, 7 factorial multiplied by this combination, in which this number is 7, it becomes nothing except p 17 and 7. This multiplied by the last one also becomes p 12 and 6. So if you want, you can write it like this. So in principle, I could have asked this question before even starting talking about combination, because you can view this as just a permutation. If you want to see it as a permutation, how could you see it from the beginning? So the reason that I solve this problem in this way, because I want you to see sometimes for human brain, thinking in that way is simpler than thinking in terms of permutations, yes? But if you understand it, if you have a deeper understanding, you could come up with this answer directly according to the models we have. So what do? You would say that, okay, I need 13 locations, but I want to arrange them alternatingly. So what do I have? I would consider physics books as 17 distinct objects, but I want to choose 7 of them and arrange them in 7 distinct locations. Do you remember? That's exactly the model of P. And I will do another P for the second one. So you can think in terms of P for this problem, or you can think in terms of combinations in this problem. Which one is more suitable for you? It's better to have these tools in your toolbox so that you can change your perspective from a problem to another problem. Yes, is that clear? Okay, so if it is a good idea, if I want to construct such a model for combination, can you imagine what that model is? I mean, the marbles and boxes. The marbles and boxes are good models. So if I want to construct such an abstract model for combination, what do you think? So do you remember what I mean? So we had n distinct marbles or distinct objects. Or distinct boxes. Okay, R is maximally n. The number of ways that I can distribute these n objects into these boxes, in which every box receives exactly 1 marble, is Pn and R. Yes, it was the model. And then I have 1, 2. This time the marbles are R. The number of marbles is R. And then the number of boxes is more. But still, the marbles are distinct, the boxes are labeled, so they are distinct, and I want to distribute the marbles within the boxes in a way that each box receives at most 1. Yes? Again, the answer to that problem, that distribution problem, is the same. So these are the marble box models for P. If you want to imagine such a scenario for C, what do you say? For example, let us stick with the first one, yes?
You have 10 marbles, and then you have one big box that has places for many marbles.
Yeah, exactly. In other words, the boxes are not labeled. So the boxes are distinct. So if you want to see, this is your scenario. Of course, it is not a very good model. It's not very effective like this, but you can imagine it like this. So I have n distinct marbles, but I have how many boxes? I have r boxes, but it doesn't matter which box is which. It's hard for a human to imagine, you know, because even the boxes are identical. We can keep track of that. I have two objects. So, for example, if I start moving them around, and if you have a sharp vision sight, you can keep track of them. But you know that this is not in quantum mechanics. In quantum mechanics, two electrons are really identical in any kind of meaning. So it means that it is not possible to recognize them. For billiard balls, I mean, if you can take the video from them and you can keep track which ball is going where. But this you cannot do with elementary particles. Okay, so here, imagine that they are identical in the sense of quantum mechanics. There is no way that you can understand which one is which. If you have such a scenario, you can use C or an R. Okay? So if how many of the boxes you have, you only know that you have R number of boxes, but the boxes are not labeled. Okay, what is the analog to this one?
The marbles aren't labeled.
Marbles are not labeled, and how many of them are there? Yes, so this time, if I want to see, let me see. Yes, there are R marbles, you can say quantum mechanically electrons, which are completely identical, but R of them. But this time your boxes are labeled. Yes, so the boxes are N and labeled. And then what is your goal? Your goal is to distribute the marbles within the boxes exactly as before, so that each box receives at most one marble. Okay? So again, the answer to this is the same. So I don't know if it is not a very good model like this. This is very tangible because it's according to our human intuition. But here you have to imagine that the boxes are not distinguishable in any sort of way. Okay? Okay, now let us try to solve a little bit more interesting problems. So to do a project, let me write the important parts. I don't want to write all the sentences. It takes a long time. Okay, so the question is this. To do a project, we need to have a 4-member team. Okay? So we want to construct a 4-member team. Okay. For this, we have 5 female candidates. So number of females is 5. And the number of males is 8. Yes? Okay, in how many ways I can set up this team if at most 2 men can be chosen? Okay, I want you to think and solve it yourself. So the question is that I have 5 female candidates, 8 male candidates, and I want to set up a team consisting of 4 members, but I have some restrictions. The restriction is that at most 2 men can be chosen. You need more time or you are finished? The problem is not hard, yes? Which part of the problem indicates that this is a combination problem, not a permutation problem. Yes?
It's a 4-member team.
Team, yes. And then we don't have different roles in that team. Of course, if you want to choose one of them as the boss, the other ones as different positions, then it becomes a permutation problem. Because only the choice will not be matter, because when you have your combination of 4 people, then you want to assign the particular job to each one of them in that team. Okay, but that's not the problem here. So having a 4-member team is already indicating you that this is a combination problem, not a permutation problem. But the constraint tells you that you are allowed to at most choose 2 men. So how do you think? At most 2 men means? Yes?
First consider the scenario where you choose no men, and then only 1 man, and then 2 men.
Only 2 men. And then what do you do with these numbers at the end?
Add
Add them. Is that understandable that you have to add them? Yes? So I would say that because you are telling me that at most 2 men should be involved, I can say that, okay, let us get rid of men and then choose only women. So in how many ways I can set up my team consisting of only women? Because I have 5 of them, I choose 4 of them. Yes? So I would say that I have 5 distinct objects here, females, and I want to choose 4 of them. This is one scenario. In this way, I am setting up my team consisting of only females. But this is not the only option. I can choose 3 females. This is important to understand. So how should I write that? So this is, you see, I would say that I choose 4 out of 5, or when you say or, it's an indication of addition. And then what do you say? From the females, I choose 3 this time, but I choose 1 man. So, and it means multiplication. And how many men are there? 8. I choose 1 of them. Yes? So I hope that you are not confused between addition and multiplication. Yes? And then or, what do? I choose 2 ladies and 2 men. Yes? This is the answer. Is that right? So we can calculate them. By the way, let us do once this. If I want to calculate this, it becomes 5 factorial, 4 factorial, the difference between them 1 factorial, plus this becomes 5 factorial, 3 factorial, the difference between them 2 factorial, multiplied by 8 factorial, and then divided by 1 factorial, the difference between them 7 factorial, and then finally 5 factorial, 2 factorial is the difference between them 3 factorial, multiplied by 8 factorial, 2 factorial, the difference between them 6 factorial. Okay, so can you do this one in your head? 5 factorial is 5 times 4 factorial. So 4 factorial is gone, 5 is left, because 1 factorial is just simply 1. 5 factorial is 5 times 4 times 3 factorial. 3 factorial is cancelled. 5 times 4 is 20, divided by 2 is 10. Multiplied by, what is this one? 8. Because by the way, we know that I have 8 people. I want to choose 1 of them. In how many ways I can do that? 8. So this is 8 plus, this is the same number. The only difference is that this is flipped. So if this was 10, that also becomes 10. So what happens here? 8 times 7 divided by 2, which is 28. So this becomes 80, 280, 365, yes? That's the number of days in a year, yes, so it's that accident. So we can calculate, we can choose this. Okay, the next question is more interesting. I want to wait a little bit for you. The next question is, I give you only 5 digits, 1, 2, 3, 4, and 5. So you are not allowed to use any other digits, but you are supposed to construct. So 1, 2, 3, 4, and 5. These are the only digits you are allowed to use. And then you are supposed to construct a 7-digit number. 1, 2, 3, 4, 5, 6, 7-digit number. Okay? So that, what is the question? So that each one of them has exactly 5 odd digits. Each having exactly 5 odd digits. So you have to analyze the problem yourself first to understand if repetition is allowed or not. These kinds of questions is clear from the text. And then you solve it. Okay, I want to wait for you. Could you come up with an answer? Yes, you want to say something?
I was gonna say 10.
No, it's much more than 10. I don't know the number. Just give me an answer so that I can write it down. Yeah, just at this level. You don't need to calculate the details. Yes?
I have P of 5 and 3.
Let me write. P of
5 and 3.
only
And then times 2 factors.
times 2 factors. I don't think this is the correct answer.
I wish it would matter.
No, the question, you shouldn't ask these questions. When you want to write a 7-digit number, do you think order matters?
Yes.
So order matters, yes? Might be this answer is correct, I don't know, but this is not my, at least, intuition. Any other solutions? How did you think about this, that you come up with this number?
I thought we need to choose 5 of the odd numbers. We have 3 of them.
No, this model works if the repetition is not there. Yes. So you are saying, so I don't understand when you say 5 and 3, what is 5 and what is 3?
5 is the number of odd digits that need to be in the number. And then 3 are the odd digits we have to choose from. 1, 3, and 5.
No, because we don't have 5 objects.
We have. Is it we have?
We have only 1 as an odd digit, 3 and 5. So these are odd objects that I have in my hand.
So we have, and we need to have 5 odd digits.
Yes,
That's the
so
number of
but then
boxes.
it means that I have to repeat at least one of them, and then this model will not work. So do you understand what I mean? Because if you want to use, in this model, boxes and marbles are all distinct, but it is not possible to have a 3, because if I want to write 5 odd digits, so what happens? It might happen that I cannot choose 1, 3, and 5 because I do not have enough odd digits. So it means that I have to repeat that. And it means that either my marble is not distinct or my number of boxes is not distinct. Yes. So it is not possible to use that model. So that model is very unforgivable. It should be exactly according to what is written there. Okay. So let us think about it. How do you think about the problem? I would say that I want to have 5 odd digits. Yes? So what I will take my marker and mark 5 of these locations. Okay? So for example, this, that, this, and that. I can start changing these green markers. So these, I'm just saying that stage 1, this is my story. You can come up with your story if it works. My story is that first I find the locations, I determine about the locations of my 5 odd digits. These are just locations. So I want to take my marker and cross them over. When I want to cross them over, it means that my marbles are not distinct. Is that right? Because my marbles are these green crosses, so they are indistinguishable. And then my locations are 7 and they are distinguishable because this is location 1 in my 7-digit number, this is location 2, etc. So you see that one of these models will work, yes? This one. My marbles are those green crosses, they are indistinguishable, and I have 7 distinguishable locations. So that is not a permutation problem. This, if this is my story, okay? So stage number one is the number of ways that I can do these 5 green crossings. So according to the model we just described here, the answer is what? How many boxes I have? 7. The boxes are distinct. The marbles are in the same, identical. So it becomes 7 and 5. So far, I have determined, I made my mind at which locations I want to put an odd digit. Okay? Now, what do you say for the story for stage 2? Now that I know where I want to put the green crosses, I know the green crosses where they are. I want to put odd digits in green crosses. So, how many ways I can fit this up? 3. And this? 3, 3, 3, 3. So it becomes 3 to power 5. Yes? So this becomes 3 to power 5. And after this is done, stage number 3 is fill up the leftover locations with even digits. Okay? These are the leftover ones. How many ways I can fill it up? 2. And then the next one? 2. So it becomes 2 to power 2. So the answer to this question is what? Is 7, choose 5, multiplied by 3 to power 5, multiplied by 2 to power 2. So I would say that this is a good problem. First of all, it's not that hard, but hopefully it will tell you that why we should use this model. And as you see, this is probably a real combination problem. Here, unfortunately, I erased that. Do you remember we had a problem here that after we solved the problem, we realized that we can use the permutation problem. So it means that there, I really had 2 choices. But here, this is a real combination problem, because if I multiply this here, it will not give me a permutation. So this is neat. Is that clear? I hope that you understand that why this doesn't work. Yes? Any questions? Okay. Now, do you remember when we were dealing with number theory, we had a problem that it was the number of diagonals of an n-gon, a polygon with n sides. We can now use combinatorics to come up with that answer much easier. So let us ask your opinion about that. So let us try to solve some geometry problems here before going to that. For example, let us say that I give you a circle, and then I just randomly pick 10 points. 1, 2, 3, 4, 5, 6, 7, 8, 9, I don't know, 10. Can you tell me how many line segments I can construct using these 10 points? Just tell me, you don't need to calculate. I want you to see, I want to find a line segment. How many ways I can construct a line segment? So for example, you can decide to connect this to that. This is one line segment. You can decide to connect this to this. It's a line segment. So how many red line segments you will be able to draw if you consider all possible cases? In other words, do you think it's a permutation problem or a combination problem? It's a combination problem, yes, because if I give these names A, B, C, D, E, F, G, H, and I, the name of this line segment is AD or DA. I don't consider them 2 different line segments because AD and DA are representing the same line segment. Okay, so you see that the order in which I put the names does not matter. So if I ask you what the answer to this question is, what's the answer? How many line segments I will be able to construct? 10, choose. Yes? Okay, now question is that how many vectors I can choose? I can construct. How many vectors I can construct using these 10 letters or 10 points? This becomes a permutation problem, yes? Because it matters if you say vector AD or vector DA. Line segment AD and line segment DA are the same, but vector AD starts at A, ends at D. Vector DA starts at D, ends at A. So they are opposite, they are not the same. So this becomes a permutation problem. So for the vectors, instead of 10 choose 2, I have to write P, 10, and 2. For the vectors, it's clear. Let me ask you, how many triangles I can construct using these 10 points? Yes?
10 choose 3.
10 choose 3. Why? It's because you know that for a triangle, so for example, let us choose this one. I need to choose 3 points. I need to choose 3 points to construct a triangle, and it doesn't matter how you name it because triangle ADG and triangle AGD are not distinct triangles. They are the same triangle. So that's not a permutation problem, that's a combination problem. So the number of triangles is 10 choose 3. The number of triangles is 10 choose 3. One question here, do you think it matters that the points are on the circle in order to solve that problem and say that the answer is 10 choose 3? Could 10 points just be randomly on the whiteboard plane and ask you the same question and you can answer the same answer? Yes?
No,
Why not?
because if you have 3
Points on a straight line, it's not a triangle. So it doesn't matter if it is on a circle or not, but mentioning the points are on a circle is an indirect way to telling you that no 3 points lying on the same line. So it means that you are confident about that I will not have that scenario that you mentioned, yes? Because if I give you these points and I ask you how many triangles you can construct using these points, none. Yes? So that is an indirect way to tell you that the points, no 3 of them lie on the same line. So yes, that was a little bit important. Okay. Now let us say that I have an n-gon. I want to count the total number of diagonals using this idea of combination that we learned today. If you remember, we solved this problem using a different technique, mathematical induction, to prove that the formula is this. Do you remember what was the formula? The number of diagonals was n times n minus 3 divided by 2. This was the number of diagonals of an n-convex gon, yes? But we proved this using mathematical induction. So in other words, someone gave the formula to us, and then we were able to use mathematical induction to confirm that. But now, let us derive it using the idea of combination. So how do you think about the problem? So you can consider an n-gon. So vertex number 1, vertex number 2. So when you say I have an n-gon, it is already guaranteed that no 3 of them lie on the same line, yes? So A3, A4, and then let us continue A, n minus 2, A, n minus 1, and A, n. Something like this. Imagine something like this. Okay. But I want to count all possible diagonals. So if I have an n-gon, this is your n-gon, continues. Something like that. Okay? This is your n-gon. And you want to consider all possible diagonals. You want to count them. Okay. What is your strategy of counting these using the idea of combinatorics, and especially this combination problem we learned today? All possible red lines. How should I count them? Yes?
You can do n choose 2, but you also include the black line, so n choose 2 minus n.
Yes. So it's very simple, you see, because when you say n choose 2, what are you counting? All possible line segments. Yes? You are considering all possible line segments. You are considering A1, A2 as well. You are considering A1, A3, of course, but you're also considering the black lines. The black lines is not the ones that we want to count. So I would say that when I do this, I am considering all possible line segments, but I know that the black ones are how many? Because that's an n-gon, there should be n black lines. Those are not diagonal, so I will take them off. That will be the formula. But let us see that, is it really that formula that we had and prove it using mathematical induction? So how should I find that? I would say n factorial divided by 2 factorial n minus 2 factorial, and then I have minus n. Yes? Let us simplify. This becomes what? N times n minus 1 times n minus 2 factorial. 2 factorial is just simply 2, and then I have n minus 2 factorial, and of course I have an extra minus n here. This one and that one are gone, and I am left with n times n minus 1 divided by 2 minus n. So if you don't mind, let me factor n over 2 out. Of course here, this becomes n minus 1. What will happen for the next one? It didn't have any factor of 2. I pulled it out. So what should I do to compensate for that? What? 2. I should write the 2 there, yes? Do you agree? Because if I multiply n over 2 here, it becomes that. And if I multiply n over 2 here, 2 and 2 are gone, minus n is left. So my factorization is correct. And then, of course, n minus 1 minus 2 is n minus 3. So this becomes n times n minus 3 divided by 2. So this is, at least, I hope that you understand that we derived the formula here. In mathematical induction, that formula was proposed, we confirmed that. So this is more powerful, I would say. And that's a nice idea to see that how these things can also help to solve some geometry problems. Okay, is that clear? Okay, so let me make it a little bit nicer. So the problem is that this time I give you two parallel lines, line L1 and line L2 are parallel. L1 is parallel to L2. And then let us say that you have 1, 2, 3, 4, 5, 6, 7 points here. And then you have 1, 2, 3, 4, 5, 6, 7, 8, 9 points here. So 7 and 9. How many triangles I can construct using these points? That's the question. It's a simple question, but it is a little bit more interesting than the previous one. So I have two parallel lines. On one of them, 1, 2, 3, 4, 5, 6, 7 dots. In another one, 9 dots. I want to construct triangles using these points that you see, these black dots. How many triangles I can construct with these points? I want to wait a little bit for you. Yes? You want to ask a question?
I can ask a question. Do we also need to factor in that a line can cross through a dot?
Yes. Yes, I give you these dots. I want you to construct all possible triangles. So might be you connect this one to this one. So the triangle means 3 vertices. Yes. Okay. Could you solve it? So how should we solve the problem? We consider two types of triangles. Yes. one triangle so that the base is on this line, the vertex is there, and the other way around. Yeah, as simple as that. So if I want to consider these type of triangles, so how many of these type of triangles I can see? For having the vertex, I need to choose one of them. So it becomes 7 choose 1, or you can simply write 7. And 2 out of 9. Or the other way around. Yes, what happens? The other way around means 7, 2 times 9, 1. That's your answer. Is that right? Okay. So another problem, let us solve this one as well. That's also interesting. We have 10 people. Let us say person 1, person 2, person 3, person 4, person 5, and then up to person number 10. In how many ways these people can stand in a queue in a way that people P1 and P2, both of them, are ahead of all P3, P4, and P5. Yes, is that clear? So it means that I don't have any obligation for P1 and P2 with respect to one another. I don't have any obligations with P3, P4, P5 with respect to one another. But I want to have both of these people be ahead of all these people. Yes? Is that right?
You want P1 to be ahead of everyone else, or
No, P1 and P2, both of them should be before all three of them.
also?
But I don't say that. For example, P1 and P2 can be in the very last part of the queue, but these people should come after them. Yes, that's what I'm saying. So is the question clear? So P1 and P2, both of them should be before all three of them. That's the constraint. Okay, any ideas? Was it hard? No, okay, I will give you a little bit more time. It's not hard. Okay, so let us solve it because we are running out of time here. So I don't know, in principle, how many locations I need for arranging these people in a queue line? 10. Yeah, so let us just think it this way. But the locations are distinct, remember. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. The way that I cook up my story is this, okay? I would say that I will take this green marker and then fix these problematic people. So how many of them are there? 5 of them. So I will take my pen and cross 5 locations. Okay? So for example, this one, that one, this one, this one, and that one. For example. In how many ways I can do this marking? And that's exactly the model you see. I am giving the role of marbles to these green crosses and the role of the boxes, which are distinct to these 10 distinct places. The places are distinct, the markers are indistinguishable, and then I have to use the combination model because when the marbles are indistinguishable, that's okay. So stage number 1, I ask myself how many ways I can do this crossing. That is exactly that model. So the number of ways that I can do this is 10 choose 5. Now, stage 1 is done. It means that I decided about the locations. Now, what do you think I will do now? Stage 2?
Find out where P1 and P2 are.
Yeah, I have to put P1 and P2 in 2 of these locations, and P3, P4, and P5 in the rest. But then I have an obligation that P1 and P2 should come, all of them, before all of the other 3. So how many ways I can do that? So I hope that you agree that the first 2 locations should be dedicated to P1 and P2. In how many ways I can do that? Yeah, it is 2 factorial, or 2. Yes, so stage 2 is 2 factorial. Now, what does it mean? I decided to put P2 here, P1 here. I fill up the rest of this crossing with the other 3 people. In how many ways I can do that? Because automatically, I am not worried about how to arrange them. I considered the constraint. I respected the constraint because P1 and P2 in any way is coming before them. So stage number 3 is what? 3 factorial. Now, these problematic people are settled down. For example, this is P3, this is P5, this is P4, for example. And then I have to fill up those empty spaces, and that is factorial model, yes? Because how many objects, people are left for me? 5, and how many distinct locations? 5. So that becomes a stage number 4, so it becomes 5 factorial, okay? So what you you didn't say anything here. So, and then I have to multiply them. So if I multiply them, what happens? The answer to the question mark is 10, 5. If you don't mind, let me write 5 factorial first, and then 2 factorial times 3 factorial. So that's a good question. But I don't know if you, I mean, combination is from our brain, the brain structure that we have is easier to understand. But of course, this can be written as a P as well, yes? So if you can come up with a story that you directly tackle the problem using P, that's also okay. But do you have any story for that? Because this times 5 factorial becomes exactly this, and then you write 2 factorial, 3 factorial. In principle, we should have a story in which we can come up with this answer directly. But at least, first of all, tell me, do you understand what I told you here? That's one story which gives rise to my answer. That's correct answer. But then I see that this combination becomes this. Now, can you see that we can come up with this permutation problem directly without going through the combination first? Yes?
We arrange the problematic people in the queue first, and then the 2 first spots that are empty, we arrange 1 and 2, and then the 3 spots that come after that are still empty, we arrange 3, 4, 5.
It should work. Can you repeat? So because it is. So what you are saying is that what is the interpretation of P10 and 5? If I want to solve it using marble, so it means that out of those 10 locations, what you are doing?
We're putting in 5 marbles.
But 5 distinct marbles. Yes?
Person 6 through 10.
So I don't, that is not understandable for me exactly. Because when you say that, this number takes care of okay. So this permutation is on the permutation of the boxes, not on the people. Yes? Is that right? Because when I say that I have 10 locations and then I want to choose 5 of them and arrange them. And then, okay, so you say that these are the people that are not problematic here. Yeah, so might be that is a coincidence that is the case. So you say that, okay, I have the people who are not problematic, the number of boxes is more than the number of marbles, but all of them are distinct. So this is the number of, yes, that's correct. Exactly. So that is, yeah, I was still thinking about the same people. No, you are right. So we can think in this way that, okay, I have 10 distinct boxes. I have these distinct marbles. I take them and put them in 5 places. That is the model that we had. But yes, I can use this. But then after that, there are 5 empty places left for me. The first 2 should be filled with P1 and P2. The rest should be filled with the other 3 people. So that's also correct. So if you have thought in that way, you can come up with this simpler answer directly. But I hope that you agree with me. Sometimes thinking in combination is somehow easier. I don't know, for my brain might be. Okay? So that's why it's better to see both perspectives. Any questions? Thank you very much.